Hello, everyone, and welcome to the recorded version of the Emag Exam 2 review for 3407. I know previous week there was an exam review I hosted as well. That was turn one. That one turned into more of a Q&A session. So here I am going to cover a new set of problems and probably touch a few on the previous ones I did. But yeah, let's get right in it, honestly. So for my exit, that's why I thought I was gonna bring me back up. Unfortunate. It is fine. Just bring that up. Bring that up here. There we go. Okay, I'm just gonna leave this here in the corner because I don't think I can take it out. Yeah. Oh well. Okay, that's just gonna be there. Hey, we got a 50 ohm lossless transmission line to be matched to antenna load using a shorted stub. That is crucial there. Okay. Let me change the color and put this in the bottom right corner instead. I want to know that this right here is important, okay? Shorted step, antenna load impedance is 70 minus 34J, and the lossless transmission line uses dielectric material with epsilon R 2.6. This is also important. I'm not sure if you guys have worked with this before, but we're going to find out together if you know the reasoning and equations we'll be using for this problem. Time monarch generator voltage is equal to 100 volts, and our generator impedance is equal to 50 ohms, connected through an antenna that's 10 meters long, and a guide wavelength is 1.75 meters. We're giving it in meters. Crazy. He might do to watch a Dr. Watcher might do that to you guys, but we will find out how to interact with this. So, biggest thing is first we want to find the VES. Okay, it's gonna be some meter value between the load and the stub. So all we're saying is we want to find L of S and E of S in meters, right? And specifically the shortest distance. Okay, so now that we have that in mind, let's go ahead and get right to it. So first thing first, okay, I'm just going to write a few equations down, see if you knew that the questions above, how they were phrased, led you to this, right? So all I'm saying is this right here, epsilon r, this is getting pulled from your chapter 1, and here is a fun little thing that might come in handy. We don't need to know frequency, okay? If you're jumping in that direction, that's fine that you understand that, but is not needed for this problem, right? Is not needed for this problem, at least from my understanding right now. Okay. So, first thing first, I'm going to just write that one. I'm going to write our distance equation, or at least one of them. Let's see if you can catch where I'm going with this. There's that one. And then, okay. So this time around, what we're asked to find is the stub distance and stub length. Okay, so just to iterate what that means. Basically, all I'm saying is on some transmission line, right, there is going to be some stub, right? It's here where we want to find two things, okay? And I'm just here drawing it a little bit darker so we can actually see what's going on, right? So this distance right here is essentially our length, LS of the stub, and the one that's actually on the transmission line, this is our D of S. Just to better visualize what we're actually trying to find, right? So let's go ahead and get in right into it. So the first thing the book does for you is basically you normalize it, right? So I'm going to go ahead and follow the book format this time around, okay? We normalize it using y z naught over zl. Okay. Um, I'll be showing some of the math, not all of it though, because I just didn't feel like doing all of the math this time around again. But it's just to show you what value you should be getting, or if you can find any mistakes I made, because who knows if I made mistakes on these problems. 28071J. Okay, that's that first line of math, right? So what's next? Well, you usually want to find gamma. Gamma in this case is just 1 minus our normalized over 1 plus. Okay? And then so I would be careful on two things, right? So you can work with either the basic um, rectangular form, right? You can work with that, or you can work with the polar form. It just depends which one you want to do, but just know that you can, for theta r, you can find that in either degrees or radians, okay? Just stay consistent because I'm here looking at my notes right now. I converted between the two, actually, between degrees and radians. Just please be aware on how to manipulate both forms, okay? Because for analysis, we can use either or. I'm not saying one or the other is correct. Just use whichever one you want. So now if whenever you find your gamma, we can go in and really start going to this, right? But for the sake of this, I do actually have a gamma value we can use. All I'm going to be saying is 3.1627 e to the negative j point 76298. And I'm also going to find the equivalent form of it, which is just really just a quick conversion, right? If we're going from radians to degrees. So it just really depends which one you want to use. Again, just stay consistent. That's what I'm saying, okay? This value right here is your theta r. And you do carry over the negative, so please keep that in mind, okay? And we have that, okay? The book explains like you have to find your acceptance, your G of S, B of S, all these equations, right? I'm going to simplify it down for you. Really, the next step is, okay, you want to find theta prime, right? Theta prime, all that is equal to is really the cosine is equal to, let me go ahead and pull up some other notes. Just give me 1 second to verify a couple of things. Mm, yeah, just want to make sure I was going to write that equation down correctly. So we're just saying find theta prime is equal to cosine inverse of our magnitude of our reflection. But guess what? We already have that value here. So literally, you just kind of go through and just plug and chug there, right? So, but really what that means is the magnitude is just the real portions of it, right? Because that's all it becomes out to. So it's this specific 0.31627 number we'll be plugging in there. Let's go ahead and buffer it. So I'm saying theta prime is going to be equal to plus or minus 1.8926, or again, depending which flavor you want, 0.44 degrees. Again, I'm just showing it just in case you want to compare your math, right? So we have two theta values we have to compare it to now, right? Why do we have two theta values? Well, because either or one of these answers could get us the shortest distance. We don't really know until we test both of them out, right? So now I'm going to say, let's label the positive D1 and the negative value D2. So D1, distance 1, is just going to be that distance equation we wrote up here, right? This one right here. This one right here. Let's go ahead and go through. Okay, so we're going to go ahead and write it through. 4 pi minus 0.72698 minus, I'm keeping it radians in this one. You can keep it in degrees, it's your call, but we have this fine. Let me move this down a little bit. There we go. We have this fine 0.0518 meters D2 is equal to, I'm going to skip that math, but basically what I'm saying is there's going to be a sign change here for adding it instead, right? And I flipped it by accident. I did D2. This is D1, as we see the signs in the middle here. And then D2 is going to be point one, or D1, 15731 meters. Okay. So let's go and compare our two distances right now. So one distance is equal to 0.15731 meters. The other one is going to be equal to 0.50518 meters, okay? Well, magnitude-wise, just by straight number, D1 is shorter. So we use that number right there. And that came from using the positive number. So now we know, okay, we want to use the positive theta prime. In this case, for us, is going to be equal to 1.8926. Okay, now that we understand that, what's the next step from here? Where do I go from here, right? Okay, well, there's no real good way around this. There's no real good way around this, but let me go ahead and let me not do that page. Let me go and add in the better one. One squared paper, if I can find it. That one, letter. There you go. Just go ahead and just take this one out. I don't want this one in here. Done. I don't know why it does that sometimes. Okay, now. Okay, this grand old equation. I hate it a lot. I'm not saying it's wrong or if it's incorrect or nothing, but we're gonna have to use either way. We want to find the B of S equation right here, which is that 2 magnitude of your reflection sine first sine of prime 1 plus. This honestly isn't that bad of an equation if you pre-program your calculator to go and plug and chug, or if you just are fast with the inspires that way. But I would really recommend writing on this equation. I'll make a list as we go when we start writing all these equations, right? Okay, so here is this one right here. Okay, now when we actually plug in our BS value, you should get negative 0.667 I missed up the number. 0.66678. Okay, now we have our BS value. We have to now find our lumped element. When I say lumped element, I mean it's basically saying, okay, how do I know what this is going to be? Because typically it's going to be either a inductor or a capacitor. Let me actually just write it down. Inductor or a capacitor. Okay, typically I misspelled the word capacitor, but do not care right now. How do we actually know whenever we look at it? Well, there's a quick way to indicate how this actually works. So, when we want to find our z of s value, we just real quick plug and chug, all right? All I'm saying is really z naught is equal to the, or z of s, our stub, is going to be equal to whatever our b value is, right? And then in this case is going to be this times J.66678 negative value there to get 74.987J. Okay, notice that this is a positive value, okay? That is extremely helpful for us to go ahead and identify what stub we're going to be matching. Okay, typically, whenever our Z stub is positive, it normally indicates an inductor. It normally indicates that. Whether or not it actually matters depends on Dr. Tawacha, because notice here, we want a shorted stub. That's why I made a notice. This is coming back to us. It's a short stub. Well, what does that typically mean, a short? We're typically just putting a wire across. Well, which one of these typically behave as a inductor versus a capacitor? Thought about it a little bit now? Well, it comes back down to just behaviors, right? Whenever we put a... Ooh, my bad. Let me double check before I finish this thought. Inductors typically behave as a short whenever, current goes through it, right? We learned this kind of back in circuits 1, right? And then a capacitor kind of acts as an open until voltage flows through, right? All the way around, I'm crazy, yes. So whenever a capacitor is fully charged, it's going to behave like a short circuit, and then an inductor, until current flows through, is going to behave like a open, right? Well, now that we know that, we can go ahead and, in future, understand which one to use for an inductor versus a capacitor. Okay. Now that we have that notation, or at least just the idea behind it, right? We can go ahead and continue our math. So let's go ahead and use the following. Give me 1 second. Okay. So then L of S should equal to L of S, at least the equation I'm going to be using, this one right here, 2 pi cotangent of -1 z of S j z naught all over that, right? Because I'm going to go ahead and cheat and go back to our textbook. There's a few equations you can look through and manipulate on your own time if you really want to. But the biggest ones I want to show, let me find it in the book just so that I have it. Yeah. So, where this equation really comes from right here, it comes back to these two equations. Because these right here can be manipulated to finding our length. Okay, you can manipulate these equations to find your length, right? To at least isolate it, right? So if you can isolate your length from both these equations, you have your length equations at least determined for an open and a short stub. Simple as that. The actual derivation itself isn't too bad. It's just algebra, so I'm not going to actually show you it. But we do have one of them right here, though. It's this one. I am showing off the wrong equation. Well, yeah, I showed off the wrong equation. My bad. You're supposed to use this one. You're supposed to use this one right here for this problem. That one. You're supposed to use that one there. But nonetheless, we do have our final answer of LS is equal to 0.27371 meters. So part A of this problem is going to cover, we have our distance and we have our length. Our distance and we have our length there. The actual time average power delivered that is pretty straightforward in my opinion. Because all it really is just going back to how do you solve a single load transmission line problem now, right? We just go ahead and go through and essentially say, hey, if you know your voltage at your generator, if this is known, you can find and treat your load, this is our ZS right now, ZS here. You can treat this, the voltage at your Z of S, your new generator. Because all it really is just looking at the power. We're not even looking at anything else. We know our load already, which thought makes this a lot easier for us. So we're essentially just finding voltage here and then treating this as our generator to go ahead and say, okay, now let's actually find the power across ZA. Because the voltage here is what's getting supplied on this second, the smaller branch between here. I wish I had worked this problem out a little bit earlier, but I didn't have the time to because I wanted to touch bases on a few other problems because I heard S11, understanding that behavior was something that we struggled on this year. So let's jump right into that. But just to reiterate, the real main equations take away from here, in case you're given your dielectric material, you need one of these equations, something that involves the epsilon r. You need your distance equation, really, where distance could be plus minus there. Your admittance, this is pretty basic. This one right here is also pretty basic to use. This cosine one, essential to go ahead and solving your problems, because if you don't have that down, then you're kind of lost in the water. Um, and then this final equation right here, this one's pretty important. This Z not, I didn't actually write that down, so let me write it over here. Z of S is equal to Z naught negative J, not negative, it's just JBS, JBS. And then whichever length equation you want to derive for, you can go ahead and just use whichever one there. And that will get you your open or your shorted stub there. Those are the equations there. Let's go ahead and move on to the next problem. Not the next problem, it was this one, because this was the fun one that I want to show off. The diagram below shows antenna with impedance connected to a 50 ohm lossless transmission line with length 7.3 meters. Ooh, we're given meters again. Two problems where we're given meters. Who knows if that's actually going to be on your guys' exam. We'll find out together this upcoming Thursday. VNA measurements at the input of the transmission line gives S11 is equal to 0.2 e to the negative j 0.4 in volts per volt. Wavelength on the transmission line is about 15 centimeters. Determine the antenna impedance, and then single step impedance match to the 50 ohm transmission line. We want to find the closest distance and length of the short circuited stub. Well, problem kind of covers it already, but this is a pretty quick one per se. It may be worth 40 points for this problem. I'm going to show you how quick this one can be, okay? So this diagram is given, right? We're given here. The biggest thing students get tripped up on is, well, what does S11 really equal to, right? Because the lab makes you think it's just equal to gamma, right? Physically though, right? What the VNA shows us, so I'm just gonna do this VNA, right? So typically you have some SMA connection going through, right? Okay. It goes through your coax cable. It goes to some load down here, and that's all it really sees, right? Well, this portion right here, the one in red, all that is showing is really that's your transmission line. going to your load, wherever it is, and comes back, okay? Whenever we calibrate the VNA with our transmission line in it, we're actually shifting it in and just saying, okay, ignore the transmission line. All this is saying is, hey, there's now a load on you. Let's go ahead and do it like that, right? That's what's going on here. So let's go ahead and figure out what is going on here. The S11 equation you should be using is this one right here. Zn minus Z naught over Zn plus Z naught. Which basically just saying where Zn is just equal to your shifting inwards, right? You're going to shift this and ignore the transmission line and say this is what S11 is going to be equal to, right? Where you can actually manipulate this a little bit more. That's equal to S11. We're given S11. What do we actually want from here? We want the Zn value. That's what we want, okay? Through some algebraic manipulations or just using your calculator, whichever one you want to use, you can write this equation down if you want. It is your call. S11 plus 1 over 1 minus S11. Okay? And this is the equation you go ahead and use here. So we're going to set this equal to, we have a value, it's crazy. There you go. And this is equal to your S11. Or no, not your S11, your Zn. Apologies, your Zn. Okay. So now that we know what Zn is equal to, we can go ahead and shift this back out, right? And however you want to shift it out is up to you, because that's not the goal of this problem. I'm not asking you how to actually find this, okay? Because shifting in, shifting out, that should be something everyone should be down pat with already. But let's go ahead and cover it here. So whenever we go ahead and want to find our voltage, okay, let me just go ahead and double check, make sure I have my equations down. Yeah, so depending on how you look at it, right? So Zn could be equal to a lot of things, right? You could do that weird normalized load, if I can write it better. So it's like the ZL normalized load, right? Use this equation. You can use the other one with tangent, or not tangent, cosine and sine. It just really depends which one you want to use. This is one of the many equations we can use. You can also, if you know how to use this one, you can use 1 plus RL, 1 minus reflection, right? You can use that one. You can use, let me just to prove a point. Let me just show you a different equation as well. What you can use to shift in your load. Yeah, where this is really just equal to 1, not that. Z naught, 1 plus this e to negative j, 2 beta L, all over 1 minus F, got 8. This right here, e to the negative j 2 beta L, right? You can use these equations right here. Or if you really want to be a little more fancy, here's the cosine sine one I was talking about, where basically Zn is equal to Z naught. This one's the bigger one. I like this one more because you can't really go wrong with it, honestly. Because just how the behaviors of sine and cosine, it oscillates and forever and ever, and there's no real region where it's technically an asymptote because of just if you were to graph where your answer can lie on, tangent is bounded within a certain region, and sine and cosine isn't, which is why I prefer using this one right here. But again, they're basically the same thing. Just understand how you're going to manipulate it and figure out how you're going to actually shift it in, right? So now that we have a bunch of these equations written down, doesn't really matter which one you want to use, just solve for it, right? So using this, right, we can find our z of L. Any of these to solve for z of L. Whichever one you want, it is up to you. But just to show off an equation you can use, you can say your load is equal to z naught. This is after just algebraic manipulation. Again, nothing too hard there. I realize I'm writing this wrong. You just got to be careful again on how you manipulate it. You can pre-derive it if you want, actually, just by going through the actual manipulation yourself or seeing if your calculator can manipulate it around for you. It just really depends what you want to do there. But just don't be afraid to rearrange equations is my biggest thing. So this is one of various forms to find z of a, right? One of various forms there, and we have our first answer, or at least a section of it, right? Z of a is equal to 47.682782 e to the s 0.3920796j, right? There's that. Okay, so now this is where it's fun. This is where I like to show these problems because it makes people really think a little bit more. Okay, so we're saying, okay, now that we have ZA, we want to impedance match it just a bit, right? Well, how do I go about doing that now, right? Like, what's the best way for this? Well, it's a little bit different because we're given it the length in meters, so we have a finite length to work with, right? Well, similar to this problem up here, we had a finite length to work with here as well. Biggest thing is lambda, our lambda values, just plug in a number. That's how simple it is, right? It's just a matter of finding a number and saying, okay, let's go and solve it. Sorry, okay, B. Okay, so using our equations from above, right? So I'm just going to rewrite a couple, not every single one of them. Okay, so that weird cosine, theta prime is equal to negative magnitude that one, right? There's that one. Oh, wait, what I can do is actually just kind of copy and paste a few of them, actually, and that's what I'm forgetting to do. Okay, so I want that one. I want to normalize it if possible, so we can take that one, our distance equation. Our distance equation right here, so let's come down here. Base, there's that one. We can find our distances. I theta r plus or minus theta prime. There's that one. There is z stub, z of s. That's what that stands for. JB of s. B of s is equal to this the long equation again. Again, highly recommend to pre-program the calculator as like a function of sorts to go ahead and get these numbers down. And just real quick check 1, 2. Easy as that. And then of course we want our gamma, not that one. Gamma is equal to ZL minus Z naught over ZL plus Z naught. Let me actually just rewrite this. This may be just me repeating things you guys already know, but you'd be surprised what people can get tripped up on about these equations. Okay, so, oh, and then of course, we're still trying to find the distance and the length of it, so we still need to figure out, okay, if it's a short circuit or an open circuit, but the problem already gives us saying it's it is a, this one actually doesn't tell us. This one doesn't tell us if it's a short or a open stub. It just tells us it's there. Wait, no, I'm crazy. There it is right there, short circuit. So we know what equation we'll be using here, but I just want to show off both so that way people are familiar with it. Okay, and then the cotangent one. Yeah. And then the cotangent one, I just want to double check up here real quick. It is going to be cotangent, yeah. And again, I may be writing something down wrong at any point of this. I am human. I verified a lot of this stuff before doing this review, so just please let me know if something's wrong in it. If I'm on campus or something. That's what it is. Again, you can drive both of these on your own time. If you really want to see how these work. There's that. And then so we're gonna go and shotgun this problem out a little bit because I don't want to spend too much time on what we already had covered, right? Okay. So I'm saying here we want the following. So our first one, right? First thing here, depending on however you want to find theta prime, we have two versions of it. So we have a plus minus 1.772152 is in radians, okay? So I just did there, plug and chug. We first normalized it. So we first normalized it, then we found the reflection coefficient. We found our reflection coefficient there, and then just plugged and chugged. Okay. Now we have theta prime. Theta r comes from our magnitude of it. So when finding your gamma, am I gonna write this down right? I'll double check some of my notes real quick before I move any further. Yeah. This e to the j theta r. That's your theta r. There's that, but again, if it's in rectangular form, you can go in and just convert it around. It's whichever one you want to use again, as I mentioned, is just up to the student. There. Okay, so we have that. So we plug and chug there. Cool. We have that value. Well, how do I use it now? Well, we use our distance equation next, right? So 1 sine theta prime, and theta r. Okay, next up, on your D of S. Both of them, typically both. The S1 and the S2, using your theta prime. Because we still have to verify for both of them, okay, which one's actually the closest, right? So then you should get two stub values of 275,859,23. In this case, we do have a lambda because again, even though we know our finite length, we don't know the length for the census. Well, it really doesn't matter in this case. I'm gonna leave the lambda factor in there. So all it really means is your length for this, right? Whatever length it is, it's going to be a factor of lambda, right? For D of S, okay? For D of S specifically, there's some factor of it. Whether we choose to work with it in terms of lambda length or in terms of finite number depends on your problem. Okay, that's the biggest thing. So if you're given a length, use it. It's gonna make your numbers easier, but just know that typically lambda gets canceled out at some point whenever you go ahead and uh, have a beta value in there, which is why in these equations, whenever you actually find your z of s there, that way it's going to come out and cancel out each other here, right? But we're given lambda length, or we're given a finite value for length, so I won't really worry about it here. There's that. Okay. Let me go ahead and actually finish off the other half of it. 0.006187887. Yep. There's that. Okay. There's two values there. Well, which one's closer? We can already see this one closer. So, well, we know what lambda value it is. It's 15 centimeters. Do not forget your units, okay? For the love of God, do not forget to include your units there, okay? Please. So we have our ds value now, okay? The next one is going to be that ds equation, okay? Bs, which is that long equation. Did I write it down? I did not, so let's write it down again, just so that everyone has it. Don't want people going in the exam without this one, right? Okay, there's that. This is a reference in the book. Okay, a lot of these equations are just pulling from the book, or it was some formal factor of it. Don't hesitate to look in the book, rearrange equations yourselves. It's going to be fine. There's our BS value, or equation at least. So let's go ahead and find our BS value and see what it is going to be. Also, I believe actually I'm incorrect here. I think I messed up a number there. Yeah, I did. It's actually supposed to be 0.49381213 lambda. That's after it's shifted in actually, because negative values, we don't really like working with those. So this is it shifted by half a wavelength. This is it just normal, but whenever, so let's go ahead and tackle these negative values actually, and why we don't like using them and want to still see positive in an integer, right? So let me go ahead and just add a page here. Okay, so just to explain, whenever you're given a ds value, say one's positive, one's negative, right? All that's saying is in respect to how your load is, say your transmission line is going to your left, if it's negative, it basically is saying, okay, put it in a section where there's physically no transmission line wire for you to put anything on, right? That's what that negative length is saying, which is why we shift this over in by half a wavelength, because it repeats. When I say it repeats, all we're really doing with this distances and such is we're just trying to find a value. I don't want to say value, a solution for our problem that works for us, because every half wavelength, your impedance is going to match. Not every half wavelength, every full wavelength, not every full. Let me take a step back. Typically, how our transmission lines work, at least for whenever we're stopping them numerically, whenever we shift in, quote unquote, by a half wavelength, a quarter wavelength, whatever it is, we're just essentially going ahead and going on a different section on our trigonometric functions. In this case, typically it's going to be in terms of sines and cosines, which is why a lot of these equations have those in there, to go ahead and find a section of our solution similar to how you would find a n pi radians. No, it's just some value n pi to find your specific value, trying to find on a, like a unit circle, right? Similar aspect. So it's pretty similar here. We're just trying to find some length where the impedance, not even the impedance, the length works for us. That's just what it is. Little not well explained topic, but all we're really doing is really looking at a unit circle and finding which pi value, essentially, in this case, wavelength value, fits for us the most, right? Well, again, horrible explanation. Do apologize about that, but let's go ahead and continue this, right? So there's that. Let me go ahead and I'll leave it down there for now. Just move this to there, down here. Okay. So LS. Not LBS, BFS. BFS is next. I'm crazy. So our BS values you get, okay, going to be 0.311687. Not that actually. 40824.829, and the other one is just a negative value of it. That's what it really is. Okay, there's that. Those are BS values. And then now we can go ahead and find our ZFS first. Because typically it really doesn't matter where you go from here if you find your Z stub first or you find your length of it. But when it, let me take a step back actually. That is incorrect. You want to find your ZFS value next. Crazy. And ZFS is just that basic equation right here. That basic equation right here. Where is it? Wherever it is. I'm going crazy right now. For Z naught. I didn't write it down. Let's write it down again. There it is right there. And in this case, there's two values again. I'm showing both values just so that you can see how close or unrelated they are. There's that, okay? And then let's go ahead and move this down here. Last but not least, I think this is the fifth step we're seeing. Find LS, right? You may have already solved the problem. Again, I'm just going at a pace that I like to go and explain things, right? So now our L of S, depending on which one you want to use, in this case, we want to find it for our short circuit because that's what the problem was asking us to do. Yep, short circuited stub. So then let's just go ahead and use the short circuit stub equation. There we go. And then our L of S value, we have two values we can go ahead and use. This is one negative again, so we are going to have to shift that in by half a wavelength or more, depending on how much we shift it in by. 188.31207 lambda, and then just to shift in a little bit more, 116.8793 lambda. Okay, so were we able to figure out what ds, our distance stub, and length of the stub? Let's see if you got it right. Because I put it in terms of lambda length. All you had to do was just plug in the actual finite value, the 15 centimeters. Did you actually plug it in right? We'll see. We'll see if you did. Because in this case, you're given both. That's what trips people up. You're given both. You're given lambda distance and the actual finite length. Whether or not you canceled out your lambda values in any of these equations right here, or if you kept it through your entire problem, doesn't really matter as long as you understand how you do it. So these are your answers. Okay, so Z of A, that's a pretty easy one. 7 e to the 0.3920796 Okay, there's that one. The event value is going to be equal to 0.04137888 meters. Last one's going to be equal to 0.2824668 meters. There you go. Whew, man, these problems are giving me a run for my money right now. But to recap, okay, so you're given S11. Don't panic. We know what to do. We know our equation. Okay, we know our equation. We know how to manipulate it to find Z event. Cool, we found that. Unshift Z in however you want. I do not care as long as you know how to do the math. Great, you just found your Z of A value. Cool, now what? Well, It just turns into a impedance matching problem. Find your theta prime, your theta r, first find your admittance, then find your gamma, depending on which one you want to use, right? So I don't want to say depending on which one you want to use. The book shows you how to use your admittance. That's great. This is just food for thought. You don't have to use admittance to impedance match, but do you know what that means when it comes to your future steps? I'm not going to explain that here. I'm going to follow the admittance, right? So our gamma equation is actually going to be that is equal to 1 minus y of L, 1 plus y of L. That's what that's supposed to be. We found that. We want to go find our theta prime, our distances, our lengths. We go through plug and chug, find which value our theta prime produces, which one works for us. We go ahead and plug that in and continue using that same theta prime value for the rest of it. We go through, find our lengths, distances, whichever one's trying to find us or tell us to find. It was a short sub in this case, so we found that, and there we go. That is that problem solved. Great. Now, the next problem, people were asking for a double load problem, so here we go. Let me double check a couple of things first before I forget. Is this the problem I wanted to do actually? Because hold on, apologies about this. Just give me 1 second to double check a couple of things first before I forget. Yeah, let's go and tackle it. Let's go and tackle it. This one's not gonna be too bad. I'm not gonna be able to solve all of it for us though. I can't give you the answers though. That's what I can do. So I have them here right in front of me. Um, let us go ahead and solve for it. Okay, so a couple things. All right, don't panic. It's a double O problem. We got this. Okay. Consider the following circuit generator: ZG is 50, cool. Z of M is equal to 30 plus J40. Z of L is equal to 120 minus 15J through 50 ohm lossless transmissions. That's our Z naught. We have locations too of where the stubs are located, and then we have our voltage across the transmission line. Well, specifically at the input, okay? Don't forget, at the input. That's the biggest thing here, okay? So, here we go. This is fun stuff, I promise you, okay? Voltage across our load. I don't even care about that right now. I just want to show you the fundamentals on how to treat two load problems, okay? So something I was taught on how to approach these, we have our big gamma and small gamma, okay? Really, what that means is, okay, there's an inner branch you're going to be working with, and then there's going to be an outer branch you're going to be working with. This is typically number one you want to try and work with, and this is number two. That's all I'm saying, okay? So let's go in and show you what I mean, okay? So all I'm saying is pretend there's not even a load right now at Z of M. We go through. First thing first, Z of L. You know it. Guess what? Shift it in. This is going to be Zn small. Okay, Zn small. Well, what Zn formula could I use? Any of the ones I showed you earlier. Okay, just shift it in properly for me. Okay, that's step one. Cool. Well, what do I do now? What you just did. I'm gonna be redrawing this diagram a lot. Just give you a heads up right now. Okay. What we just did is we went ahead and we went from this problem up here to after first shift. Okay, we shifted our first load onto the exact location of our second load. Okay, so guess what? Now we have at this exact point two loads in parallel. Even eval. Okay, well, how do I combine loads in parallel? This is impedances. You combine them normally how you would like just like in circuits 2, circuits 1, whichever one you saw combining impedances in parallel initially, right? You just combine them in parallel. It's just the actual parallel equation. Do I remember this one off the top of my head? Man, I look like a fool right now, not knowing this equation right now off the top of my head. Uh, man, I really am blanking out right now pretty hard for this. Man, I don't remember off the top of my head. Oh well, there's that. Okay, well, so then now you have some sort of new value. Okay, whatever convention you want to call it, it is your call. Okay, so you can say this. So you can do like a combination of like ZML, or just say like it's like ZX, whatever you want to call it. Right? Just understand that this is a parallel combination. It's some parallel combination of two loads together. Understand that. Okay. Well, now what? What do you mean now what? This is a single load transmission line problem. We know what to do with these, or we should at least. So after you combined your two loads in parallel, right? Shift in the first branch. Cool. Want to add your two loads together in parallel? Great. Now you have a new big load. Well, guess what? Now this is now considered your big, your RB, right? Your RB, all it is again. You're just your basic. It's just your basic. It's no, that's not that. My bad. I'm looking through my notes right now for this problem. Just want to make sure I'm shifting this in right. Yeah, gamma in big gamma, whatever we want to call it, is just your Zn. For this Zn is going to be your Zn big. Again, after you shifted it in. So there's two shiftings we do basically, right? So I'm going to redraw the entire diagram just to show you what is going on again. Step by step of what I'm doing right now. Okay. This is our ZL. This is our ZVM. Okay. ZLZM. Okay. So we have first we want to shift ZL in. Okay, so this is what it means when it says small gamma. Okay, you're gonna have a small gamma, a small ZN small. For now, there's their own two values we really are aware about, right? Okay, now we have those values. This one, gamma, will come into play later. It's specifically our ZN shifted in, okay? So we shift this in, right? We shift it in. So now we're saying at the point where our ZM lies is now where our new ZN small lies too, okay? Okay, you want to combine these two in parallel, just like you would any two resistors, essentially. We combine those two in parallel, and now we have a good old-fashioned single load transmission line problem. Okay? And then from here, just a matter of going through. The biggest thing is, I'm not sure if you guys are familiar or remember how to do these, right? You want to find B naught plus. Okay? Not that. I forgot it's not going to do that. This here. You want to find B naught plus. You want to find V naught plus, that's for whatever point of voltage you're given at. Okay, in this case, we're given voltage at the input of the transmission line. Okay, so we're saying here, the very front, we're given V in, essentially. This is where that Vn is equal to 75 minus J 7.9 volts, right? Okay. Well, how do we go about finding that? Well, it's just any old transmission line problem where we go ahead and want to find B naught plus at the negative length load, right? Let me just make sure I'm doing this right again. Looking through some of the... Yeah. So basically where Vn is going to, so this is our Vn, right? All I'm saying is, hey, remember how we have for every transmission line, this is normally reference 0. I believe Dr. Tawacha still does this. Go ahead and shift this in. We're saying this is 0 and this is our negative length. We're shifting in 0 to whatever length it is. Well, remember that equation for Vn is equal to, yeah, Vn is equal to V naught plus over e to the j beta L. Again, this is just one of the many forms of the equations you can use. There's plenty out there in the book. You probably have some yourself on hand right now. This is one of the many forms you can use, right? Where V naught plus is just equal to Vg Zn over Zg plus Zn, right? Times our what we had here originally. There's simpler equations you can use out there. I'm not saying this is the only one. There's definitely simpler equations. This is just one I can remember off the top of my head right now, and I have in my notes. You find your V naught plus, right? Okay, cool. Now we have some sort of V naught plus, okay? Let me go ahead and write down some values for you, though, so that way I don't just leave you empty-handed, okay? So, assuming we did our math right, okay, we can find a couple things right now, okay? So I'm saying, yeah, man, my throat is dry right now. So There's a reason why I like writing everything out so that I can visualize what's going on. Whether or not you guys actually have time to do that on the exam, well, it depends how familiar you are with this math. My biggest thing is don't panic. Don't panic. You've gone through this before. You worked through the motions. There we go there. We have those values there, okay? And then just to show you our big, right? So big, I'm saying big is the second branch, small is the first one, right? In case you want to have some of these coefficients already written down. 3741 e to the 2.4945999j. There's that. Okay, so there's that one, and then I want the small one as well, because you can go ahead and find gamma there too. 4948262 e to the negative 0.1230596j. Okay, we have those there. Okay, well, now what? We're trying to find voltage at our load, right? Well, that part's pretty easy, actually. And something I do want to point out, actually. Sometimes the numbering of the problems matter a lot, okay? If you notice, the second bullet was A, top one was B, last one was C. That matters. Why? Well, guess what? So we shifted in our values twice, okay? We have a voltage we can find using V naught plus shifting it over to negative length, right? We have that here. Go ahead and use it now. So voltage in, when we shift it all the way in, we have a value, right? Well, what would that actually get us? It will get us the ability to find our voltage at our first load, right? Well, what would it actually be? I have a value for you. So part A is asking for voltage across your first load. Well, to find that, you shift in, let me point it out. We shifted it in twice, right? Once with our first load, combine it in parallel, once again in our second load. And now we're saying Vn is equal to this. We have our Vn equation. We know what V naught plus is trying to be. Well, it's just a quick plug and chug from here, right? Because we're going to find our voltage in, find our V naught plus. Now that we have our V naught plus, you can find any voltage across that specific line. When I say that specific line, I mean the one we use for this mixed value, where this is the combination of our ZML plus our Zn small, right? That's what we have there, okay? The value you should be getting, if you did all your math right, cross voltage generator, not the generator, yeah, the first load, e to the 2.4938948. Okay, there's that. This is the first question part you would actually be solving, which is A. Okay, what's the next one? Find the voltage across the load. Well, how do I do that? Guess what? So here's a neat little trick to visualize, okay? The voltage at that point is also equal to the voltage of your negative length of your first load, right? What I mean when I say that is when we first shifted in our first load, ZL, okay, when we first shifted this in, we're going to the actual length value. In this case, it was going to be, let me take a step back. I'm kind of rushing into things here now by accident. Let me move this down here. Okay, so the biggest thing is you have to understand your notation, okay? I swear I'm not done drawing this dang transmission line. Okay, this may be not the last time. For sure, not the last time, okay? We have ZM, ZL, okay? Whenever we are given the problem, you have to understand how the notation's given us, right? So we're saying, let's go in and then look at it, right? The diagram gives this to us x at the generator all the way to our length. That's how it's supposed to be. And our finite length is 1.96 lambda. So what we're given is this. So we know this entire line is 1.96 lambda. Okay, from here to there, 1.96 lambda. And in between, we have x of m, 1.63 lambda. Okay, that's just quick math. With this difference of 0.33 lambda. Well, guess what? Now we have our notation we are going to use because I use the negative notation. So I'm saying 0 is starting at our farthest load. This is supposed to be where our first load location is right here. And then the final value here is going to be negative 1.96 lambda. Okay. So what I'm saying down here is our VM. Once when we shifted everything over, the voltage across this point, voltage across, well, let me rephrase that. Voltage at 0 of your load, which is at the load, can also be equal to your voltage of your load at the negative lambda length, wherever it is. In this case, we want to find it at negative 0.33 lambda, which is what the voltage is across our first load. That's the key connection people don't realize, at least initially on first glance. And that's what this diagram is going to be showing you, is basically saying, hey, we can treat, if my pen will work, there we go. I lost it. Okay, what I'm saying is you can treat this V of M at 0, or the VMM, voltage across our load, is now going to be treated as our voltage generator going through. Okay, and we're saying the Vn here is equal to our load voltage. That's how you go and solve a double load problem, at least in terms of voltage, right? Now, power, easiest thing ever, okay? The hardest part, honestly, is finding your voltages, because I'm going to just give you some scenarios for food for thought if you're not familiar enough with how these double load transmission lines can go. So I'm not done solving the problem yet. I just want to go and get this thought out. Sometimes, say he likes, so in this problem we were given both loads, right? So I'm gonna finally erase this right here, okay? Say you didn't know one load, right? How'd you go about solving that? Well, same thing. All we're doing is, though, carrying a variable across until two known equations, or one known equation, however you want to phrase it, is our unknown variables is equivalent to our known equations. We can substitute however you want, go ahead and solve it that way and call it a day. So say you weren't given a load, fine. Treat that as a variable in your math. So whenever you go ahead and try and combine it at this point right here, then tap the screen max, then say whenever you want to try and find the load right there. Voltage right here. Guess what? In your combination, you have some x variable to go ahead and go through, right? You can shift this in again until you have a way to solving that variable. You're going to be basically manipulating our system of equations here, okay? That's completely fine. I have faith in you guys to go ahead and do that math, okay? Another weird one he can give you. Say you're not given your voltage in. Okay, so there's no voltage at your generator given. Instead, though, he always has to give you voltage somehow. Whether or not you know how to use it, though, it's up to you. He could give it to you at one of your loads. One of your low voltages could be given. Would you be able to solve it then? Well, it's the same thing. As long as you understand the behavior, what your voltage is, what that voltage means in terms of your surrounding components, you'll be fine. Okay. Now here's the weird one that people don't really quite like seeing. I haven't seen him doing it in a hot minute, but let's go ahead and I'll mention it to you now. Say you're not given the voltage at a nice number. Okay. Say you're given the voltage at like some lambda value. So let's just say this is negative 1.45 lambda. Okay. Say you're given voltage at negative 0.1115 lambda. How would you work with it? Well, what we do know is we can find V naught plus. That's the biggest thing. V naught plus, if you find V naught plus in any of these problems for voltages, you're set. You can go ahead and then shift it around and manipulate it how you want, because that's the biggest thing we like to find in these problems, V naught plus. Voltage at a line, at a random point, is the same thing. Try and shift all these values in to that lambda length. Okay, whatever lambda length that is the point at that voltage. Well, guess what? You just shifted everything over to the voltage at that point because it's known. And now you have that. You can find an equivalency of, say, you were trying to find one of your loads. Guess what? You now have a few equations you can manipulate to find that, right? And that applies anywhere. Biggest key point is basically what I'm trying to say is don't be afraid to manipulate these problems around. Let's actually go through and finish this problem now. Okay, I swear drawing these diagrams is they're needed. Okay, it's to help visualize a lot of this. Okay, so you guys may have already solved the per day, but let me go ahead and give you a value right here. Voltage across our first load, V of M. Did I read that right down actually? Yeah, I did. I'm crazy. Crazy. Okay, now so we're here. We're going to unshift it now. Okay, we are going to unshift this, and now we're saying voltage at our Z of M. We know it is going through to our Z of L load. Okay, we have that there. Lost between thought. Okay, yeah. So we know voltage across our load here, and I'm saying the voltage for our load in relation to voltage our first load right here, V of M. All we're saying is going to be the negative length right here. Okay. So then I'm saying VL of negative length is equal to voltage across our load at 0. That's what I'm saying here. That's the relationship we want. Running a little short on time here just because I only set myself to get this over in an hour and a half this time. VL is equal to 52.08457 e to the 0.4875821J volts. This is your second answer for part B. C, let's go back up. This is the three-part question. All we're trying to find is time average power at our... This is a lot of information, okay? It's not that bad, though. Delivered to our Z of M and load. So we're just saying, okay, Z of M, Z of L. Find your power average. Easy, okay? The power average, we know those equations, okay? We just gotta make sure we set them up in relation to what we're trying to find. Okay, V of M, we have our voltage. We have the voltage at our load. There you go. That's your voltage across your Z of M load. P of L, same thing. Same thing. This is all stuff that you guys should be familiar with already. There you go. And I do have values for you too as well here. And here we go. We just solved a dual load transmission line problem. The biggest thing is understand how to shift in your loads, okay? I don't care which equations you use. I care that you understand the math. All I'm saying is shift it in once. Find the combination of it. Guess what? You now have a new value to work with for a single load transmission line problem. We've done these before. Shift it into whatever voltage point you're given, whether it be at some lambda length point on your transmission line, at the generator, wherever it is. Shift it into that point. Find your V naught plus. In this case, we're given at the voltage in, so we're going to shift it all the way in. We have everything else known. Everything else is known. It's easy. Okay, we go through, find that. Okay, we have some V naught plus value now. What does this mean? We can find voltage across any point in that section. Okay, because this V naught plus for doesn't apply everywhere. Be aware of that. Okay, you have to be aware of that. So let me go ahead and write some more values for you. So we have to include it here. Volt V naught plus of our big is equal to, in case you want to double check some of your math, or correct me and say, wait a sec, I'm getting a different number. Either or small 36.78 377E. There you go. Those are your two V naught plus values. You can double check yourself there, but these are verified to be correct from what I'm seeing on my screen right now. But yeah, so let's reiterate. I'm gonna go ahead and show you what I covered a little bit in the previous uh, problems, so in case you just want to see it. So I didn't cover this submatching problem. I covered a different one instead. Wait, did I actually cover it? No, I did cover it. I'm crazy. My bad. I covered that one. It's just wording's a little bit different. All we're saying is there's a region where we're locked out of. So you can take a look at that one if you want. I did cover physics problem. I do recommend looking at this. It's pretty straightforward, but all it really is, okay, is we're given square loop. Cool. Resistance of it. Got it. XY plane. Noted. And then we're given the magnetic field in intensity, okay? All I'm saying is, okay, we go through. I'm gonna just kind of talk over this, use my laser pointer to point at it. We're given this in a time domain. Cool. Let's convert it into phasor. Cool. There's that. Here's this relationship of your magnetostatic equations, I believe. I might be calling it the wrong one. Might be saying it instead of the Maxwell equation, whichever one. All I'm saying is we want the curl times the actual field vector intensity, and which is just this fine dandy thing right here. Because guess what? Calculus 3 is back. We're trying to find our curl of a determinant. Well, now, what that means is unit vector, the partial derivatives times your components of it. Okay, well, guess what? Here's the actual numerical math of what it's supposed to be. I'm saying h of z component with the derivative with respect to y, so on and so forth. Guess what? This cancels out to 0. It's a fun little trick to watch how it likes to play on you. Just be careful about that. The actual second part is just finding our VEMF. Just to come back up here, saying find our electric field intensity given the region. It's a square centered at the origin, which is just negative 0.5 to 0.5 because we're traveling the x and y direction. And then the z in the field z, this is something that you gotta really keep in mind. This right here is determined based off what field you're going through. The reason why I have these shapes up here is because he might give you a circle, might give you a triangle, might give you a rectangle or a square. I don't know. It could be any one of those shapes. Just understand how you set up the region. Okay, I'm saying it's a one area square on the XY plane with its center at the origin, which is why I got this right here. So we're saying it's going from negative zero point 0.5 to zero point 0.5 in the x direction and negative zero point 0.5 to zero point 0.5 in the y direction. That's how you get your bounds here. You just plug in your actual components here. This is your omega value you're going to go ahead and factor in with. Again, I covered this in my first review, so please look at that if you want. The z value. The biggest thing is, do you know how to do your dot products? Do you know how x, basically x dot times z dot, what's that equal? I covered that in my other one, basically saying z dot times anything, any component dot itself is equal to 1. Typically, whenever you go ahead and dot anything else against something else, so like x dot times y dot, it goes to 0 essentially, which is why we only have our negative 0.35 here. That's where that comes from. Voltage is equal to now current is equal to voltage divided by resistance, because the math right here gets us our V EMF, right? We're trying to find our current though. So we just use some quick math there to find our current there. A little very crash course explanation, but there's that one. Another problem we did end up covering is I actually know it's up here. My bad. I guess I only covered two. Hmm. Yeah, I guess I only covered two. That's why I had that here. Well, that's it for this review. Hopefully you learned something new or understand how to approach a problem now. Feel free to reach out for me. I know um, the TAs this semester aren't necessarily the best, but they still are there to help you. I'm a substitute for them in case you still need that extra push. That's how the HKN tutors are always set up as. But yeah. So thank you all for watching this. If you guys do end up watching this or not really sure. Either way, have a good night and hope you guys pass your second exams. Take it easy, y'all.